Hello and welcome everyone. Today I will be presenting EyeCLIP, a visual language foundation model for multimodal ophthalmic image analysis. This paper was published in Nature Digital Medicine, Top 1%, in June 2025 by Donli Shi, Wei Zhang, Jiansheng Yang, Siyu Huang, and colleagues from School of Optometry, Hong Kong Polytechnic University. Let's begin the presentation. Before I move on, let me summarize what's new about EyeCLIP. The key point is, EyeCLIP is the retinal foundation model that trains with multimodality of images with partial clinical reports. So it's not just learning from images, it's learning to align the modalities together and find common features between them. The table here shows the comparison of different foundation models along with their training data. PubMedClip uses about 80,000 images. FLAIR uses about 288,000 images. RET-Found pre-trains on about 1.6 million images. BioMedClip pre-trains on 15 million image text pairs. RETCLIP uses about 198,000 patients, pairs of left, right eyes and diagnostic report. Finally, the latest foundation model for ophthalmology EyeCLIP pre-trained on 2.7 million images from different modalities and reports. So even though EyeCLIP has fewer patients than BioMed-CLIP, it has richer supervision because of multimodalities of images from same patient. That's the core idea that drives the improvements. The key takeaway is performance. EyeCLIP generalizes strongly across 14 benchmark datasets, doing well on disease classification and cross-modal retrieval. The graph here shows the comparison of different foundation models with zero-shot performance on ocular disease classification. The blue bar here represents EyeCLIP showing superior performance. Here's the outline. First, I'll explain why we need a new retinal foundation model and what is missing in existing approaches. Then I'll introduce the pre-training dataset and the EyeCLIP framework, starting with the overall architecture, then the image encoder, text encoder, and the training objective. After that, I'll cover how they evaluate performance on downstream tasks and compare against strong baselines. Finally, I'll summarize the main conclusions and the limitations. Ophthalmic foundation models are still limited because most focus on one imaging modality at a time. Even strong foundation models like RET-Found are not truly universal. They're largely modality-specific. For example, separate RET-Found offers separate foundation model for CFI and OCT images. EyeCLIP addresses this by unifying 11 ophthalmic modalities and aligning them with clinical text, using a CLIP-style contrastive pre-training approach. Pre-training scale is a major part of this paper. About 2.78 million images from 128K plus participants, collected across 257 hospitals. The images span 11 modalities, matching real-world multi-exam clinical workflows. The cohort is diverse in age, roughly 1 to 98 years, with balanced gender distribution. The figure shows 11 different modalities, ranging from CFP, OCT to fundus autofluorescein, retchem imaging etc. along with the medical reports. Talking about images, they came from 257 hospitals as mentioned previously. A key detail is how they build matched sets. For each patient they align exams using patient ID and EyeSide. So you can have pairs like CFP plus FFA plus OCT for the same eye, different but complementary views. The figure shows diverse 11 modalities taken from a single patient. The dataset also contains 11,180 angiography reports written in routine clinical practice. These reports contain diagnoses, severity, and lesion descriptions, but in noisy free text form. The authors built a keyword mapping dictionary that encodes expert ophthalmic terminology. This dictionary is focused on finding disease first, then its severity, then the lesion, and finally the location. Before the method, I'll quickly go through 4 key concepts: self-supervised learning, clip-style pre-training, contrastive loss, and masked autoencoders in order to better understand the overall methodology of the paper. Self-supervised learning obtains supervisory signals from the data itself, often leveraging the underlying structure in the data. The general technique of self-supervised learning is to predict any unobserved or hidden part, or property, of the input from any observed or unhidden part of the input. In the figure you can see 2 stages. In stage 1, the model is trained with a pretext task without labels. The pretext task can be predicting the image rotation, image coloring, or predicting the masked patches. In stage 2, the trained model can be fine-tuned for downstream tasks such as classification or segmentation. Contrastive language image pre-training, CLIP, aligns images and text in a shared latent space for seamless multimodal learning. It uses contrastive loss to train 2 separate encoders, one for images and one for the text. High-level components include image encoder, which converts images into dense feature embeddings. Examples: ResNet, Vision Transformer. Then we have text encoder that converts text into text embedding. Example: Transformer Architecture, GPT. Finally, shared latent space. Both embeddings are projected into the same dimensional space. The contrastive loss function aligns the similar image-text pairs and separates the dissimilar ones. The contrastive loss is a function that ensures alignment of matching pairs and separation of non-matching pairs. Therefore, it is focused on paired learning. Contrastive loss computes loss using paired learning where positive and negative pairs are created. Positive pairs are adjusted to have high cosine similarity, whereas negative pairs are adjusted to have low cosine similarity. So for one image, the model should assign the highest similarity to its paired text, and vice versa. Over time, this teaches the model to encode clinically meaningful patterns that correspond to textual concepts. Masked autoencoders are another self-supervised strategy, but purely image-based. We hide a large fraction of patches, and the model must reconstruct what's missing. This forces the encoder to understand global context, like vessels, optic disc structure, or lesion patterns, rather than memorizing local texture. It's especially useful in medical imaging because reconstruction encourages attention to anatomy. MAE is implemented in 3 simple steps. In the first step, the images are split into patches, then some of the patches are randomly removed, based on the masking ratio. The encoder embeds unmasked patches by a linear projection with added positional embeddings. In the second step, the encoder embeds the remaining patches, then transfer these to the decoder. Finally, in the last step, the decoder receives input as 1. Encoded visible patches. 2. the tokens representing the masked patches. 3. Positional embeddings for all tokens. The model is trained using the loss between the original and reconstructed images. The overall architecture of EyeCLIP is divided into 3 main objectives. 1. Self-supervised image reconstruction. 2. Cross-modality contrastive learning. 3. Text-to-image contrastive learning. We will talk about each of them in detail in later slides. EyeCLIP adopts a clip-like dual encoder, image and text, architecture. Both encoders project their inputs into a common embedding space. The image encoder is a vision transformer that is shared across all 11 imaging modalities. The text encoder takes the hierarchical keyword representations extracted from reports. The figure shows the input modalities to image encoder, which is vision transformer, and textual reports to text encoder, along with the representation of shared embedding space. The training objective is threefold. 1. Self-supervised image reconstruction. 2. Cross-modality contrastive learning. 3. Text-image contrastive learning. Reconstruction makes the encoder good at visual structure. Image contrast makes it consistent across modalities. And text contrast connects images to clinical semantics. In Objective 1, the model sees only part of the image and reconstructs what's missing. Large portions of each input image are intentionally masked out, hiding vessel patterns and lesions from the encoder. The encoder only sees the unmasked patches and must infer the missing information. A lightweight decoder attempts to reconstruct the full original image, including the masked regions. In the second objective, the focus is to align different images coming from the same patients together and find common features between them. Each patient have multimodality of images, example, CFP plus FFA plus OCT. Images from the same eye serve as positive, matching pairs. Images from different patients serve as negative, non-matching pairs. Look at the figure. Here consider P1, Z1, P2, Z2 are the embeddings of different modalities for patient P1. All these Z1 to Z11 for P1 are positive pairs, and the rest of the modalities for other patients like P2, P3, and so are negative pairs. Based on the contrastive learning, we need to maximize the similarity between the positive pairs and minimize the similarity between the negative pairs. In the last objective, clinical reports are cleaned using a medical dictionary, producing structured keyword labels. These labels reflect disease, subtype, and lesion hierarchies. The text encoder converts these hierarchical labels into semantic embeddings. The image encoder maps each ophthalmic image into the same embedding space. The contrastive loss encourages each image to match its own text description. EyeCLIP combines the 3 objectives into a single joint task, optimized end-to-end. Each objective contributes a complementary type of supervision. Reconstruction learns detailed anatomy from unlabeled images. Image-to-image contrast aligns different modalities of the same eye. Image-to-text contrast aligns images with clinical concepts and disease hierarchy. After pre-training on 11 ophthalmic modalities plus clinical reports, the shared image encoder is reused as the backbone for downstream tasks. For supervised downstream learning, a lightweight classifier, MLP head, is added on top of the encoder, and the model is fine-tuned. The table here shows different tasks along with the datasets and images available for these tasks. The results were evaluated in 3 regimes: zero-shot, few-shot, and supervised fine-tuning in order to test generalization at different label budgets. This is important because foundation models should work even when labels are limited. They use AUROC and AUPR for classification performance, and recall at K and mean recall for retrieval. So they evaluate both predictive performance and cross-modal alignment. Zero-shot means model performs a task without seeing any labeled examples from that task. The model relies on semantic attributes and knowledge that is transferred from seen to unseen class. Few-shot means very limited labels. Model performs a task with only a small number of labeled examples. The model then uses these few samples to learn the new class, usually by measuring similarity in the embedding space. AUROC is area under the ROC curve, which measures the model's ability to distinguish between positive and negative classes across thresholds. High AUROC means the model ranks diseased versus non-diseased cases reliably. AUPR is area under the precision recall curve. This evaluates performance under class imbalance, common in medical datasets. High AUPR indicates accurate detection of true positives while avoiding false alarms. Recall is commonly used in image retrieval tasks. It asks, can we find the correct match among many candidates? It measures how often the correct images appear in the top K retrieved results. It is used to evaluate EyeCLIP's ability to retrieve matching images from large archives. EyeCLIP was compared with several foundation models. This include foundation models for ophthalmic images that are RetFound, FLAIR. Foundation models for biomedical vision language that are BioMedClip and PubMedClip, and finally, foundation models for general/non-ophthalmic vision language that is CLIP. For the task of zero-shot on ocular diseases, EyeCLIP significantly outperformed other models. The results shows AUROC ranging from 0.68 to 0.76 for DR, outperforming the second best, FLAIR, model that ranges from 0.68 to 0.72. For AUPR, EyeCLIP again outperformed other models in diagnosing ophthalmic diseases with AUPR ranging from 0.506 to 0.508 for glaucoma, outperforming the second best, FLAIR, model that ranges from 0.31 to 0.49. EyeCLIP showed superior performance in few-shot distribution by achieving best AUROC of 0.822 value with n equals 16 on ERDRED dataset, compared with previous best of 0.799, RET found. On APTUS 2019, AUROC of 0.858 compared with previous best 0.828. Similarly, for datasets related to glaucoma like papilla and glaucoma_fundus, EyeCLIP achieved best AUROC of 0.913 value with n equals 16, compared with previous best of 0.869, PubMed, for glaucoma_fundus dataset. For papilla, the model achieved a UROC of 0.791 compared with previous best 0.769 from PubMed. EyeCLIP achieved best a UROC of 0.82 value with n equals 16 on retina dataset, compared with previous best of 0.81 on CLIP. On OCTDL, a UROC of 0.96 compared with previous best 0.95 on PubMed. EyeCLIP was tested using the full data supervised learning on 11 public datasets. EyeCLIP outperformed other models for 8 out of 11 datasets. For the rest 3 datasets, APTIS 2019, MESIDOR 2, and OCTID, RET found was better in performance for a UROC. Similarly, for the AUPR, EyeCLIP outperformed other models for 8 out of 11 datasets. For the rest 3 datasets, APTIS 2019, MESIDOR 2, and OCTID, RET found was better in performance for AUPR. For zero-shot multimodal retrieval, EyeCLIP significantly outperformed other models in cross-modal retrieval. The underlying results were carried out for retina image bank across 3 configurations: text-to-image, image-to-image, and image-to-text. The graph shows bar plot. Here the blue bar represents EyeCLIP that shows best results. EyeCLIP significantly outperformed other models in image-to-image retrieval with a mean average recall of 40.7%. Compared with previous best of 32.9%, Biomed CLIPs, on angioreport data. The figure on the right shows the examples of image-to-image retrieval. For image-to-text and text-to-image task, EyeCLIP significantly outperformed other models with a mean average recall of 44.3%. Compared with previous best of 40.1%, Biomed CLIPs, on angioreport dataset. For another dataset retina image bank, EyeCLIP achieved a mean recall of 50.9% on image-to-text. Compared with previous best of 45.3%, Biomed CLIPs, on retina image bank. Ablation study shows the importance of each component inside the overall architecture. Here we can see the performance on unimodal and multimodal datasets. The mean AUROC significantly drops from 0.827 to 0.704 on IDRID dataset. Similarly for APTIS 2019 and MESIDOR 2, the greatest drop in performance can be seen by the removal of image self-reconstruction learning. This shows that self-reconstruction is an important part of EyeCLIP. To wrap up, EyeCLIP is a large-scale multimodal visual language foundation model trained from real clinical imaging workflows. It performs well in zero-shot, few-shot, fine-tuning, and retrieval, showing broad transfer and strong alignment. Limitations remain: data geography, handling of 3D/volumetric structure, and the gap between benchmark performance and clinical deployment. But overall, it's a strong step toward universal multimodal ophthalmic representation learning. Thanks for listening to my presentation. If you have any questions, please let me know.